Okay. Right. Okay, good afternoon and welcome to the fifth Fall 2009 Nokia Distinguished Lectures on Cyber-Physical Systems, which is organized by CITRIS, the Center for Information Technology and Research in the Interest of Society, and CCIT, the California Center for Innovative Transportation. So this lecture series is organized by the Intelligent Infrastructure Systems Cluster here at CITRIS. And if you're watching us online, you can, for our viewers from UC Santa Cruz, UC Merced, and UC Davis, you can IM us your questions and we will read them at the end of the talk. So I'm going to say a couple words about the Nokia Distinguished Lectures on Cyber-Physical Systems. These lecture series are funded by Nokia. And the global emphasis of the lectures is basically on systems which ally computational processes as well as physical processes. And a particular example of such systems is the Mobile Millennium system, which is currently being built jointly by Nokia and Berkeley, in which cell phones are currently used to track and monitor traffic in the transportation network. And if you're more interested by this project, you can look on our website at traffic.berkeley.edu, where you will also find the planning of the lecture series. So before I introduce today's speaker, let me announce the next lecture will be on October 28th, and we'll have Professor Bill Spencer from UIUC, who is going to speak about smart sensing technology, a new paradigm for structural health monitoring. So today we have a very particular lecture. We are very honored to have Professor Miroslav Krstic from UCSD, who is going to talk about the Smith predictor. And let me just give a brief introduction to Miroslav's bio. So Miroslav got his diploma engineer from the University of Belgrade in Yugoslavia in 1989. He has a master's and PhD from UC Santa Barbara in 92 and 94, respectively. He is currently a fellow of the IEEE and the IFAC, and he was a Springer professor visiting the ME department last year here at Berkeley. His field of expertise is nonlinear adaptive control, stabilization of PDEs, partial differential equations, and extremum seeking. Now, this talk today is a specific tribute to Professor Otto Smith, who is an emeritus from UC Berkeley. I'm going to also give a very short introduction to Professor Smith, who makes us the honor to be with us today. So Professor Smith got his bachelor in chemistry in Oklahoma State University in 1938. His bachelor in electrical engineering also at Oklahoma also in 1938, and his PhD in power and high voltage at Stanford University in 1941. I think for those of us who are in the field of control, obviously the Smith predictor is a tool that we've been using for a very long time. In fact, I think this talk almost coincides with the 50th birthday of the invention of the predictor. And so I think what we're going to hear today is a perspective on possible extensions of this predictor to potentially infinite dimensional systems. So please join me in welcoming today's speaker, Professor Miroslav Krstic, and also honoring the presence of Professor Otto Smith among us.
Thank you very much, Alex. It's a great pleasure and honor to be back here almost a year since my Springer visit last October and November. I would like to thank Alex for his hospitality in arranging this. I would also like to thank Alex and Professor Shastri for arranging the presence of Professor Otto Smith. And finally, I would very much like to thank you for joining us today. Yes, there is a very nice coincidence here that I got obsessed with some of these problems just about 50 years since somebody else probably did too. So these are some of the basics. As I said, I got into problems involving actuator delays in the summer of last year and had just produced some papers before coming for my Springer visit to Berkeley. And honestly, I didn't know actually much about Otto Smith, but Tomizuka told me a lot of things. He showed me a copy of your 1957 book, very impressive book, which he had received from Takahashi, and so on. So when Alex invited me to come speak at Berkeley again, there were many options for a topic, and some that might have been fitting more closely with the theme of CITRIS, but I decided to talk about this. This is a topic that I'm working on in my spare time by myself for the most part. So really no collaborators to mention, nor sponsors. This is certainly not something that's attracting much funding, but it's a very interesting topic. So here's an outline of what I will talk about. In the first two bullets, I will overview some of the basic ideas for linear systems and show how a perspective on predictor-based feedback using the infinite dimensional backstepping tools for partial differential equations can help establish stability and robustness properties for linear problems. Then I will talk about an extension to predictor-based observer design for systems that have a delay on the other end, the sensor end. Then I will talk about extensions to nonlinear systems and extensions to problems where the delay is unknown, long, and needs to be estimated in a feedback loop. And finally, I will talk about some extensions of the predictor-based ideas to actuator dynamics and or plant dynamics that might be some other types of partial differential equations rather than the transport PD or delay. And finally, just not to completely disappoint the network control systems people and people who expect such things in a CITRIS talk, I will talk about a new subject that is linked to control PDs in robotic swarming or coordinated motion control. So delay systems arise in many applications. I don't think I need to spend much on this slide. Probably you've been involved in at least one or more of these applications over the years. And here's what I've learned after getting into delay systems. This is a topic that started getting some systematic and analytical attention in the late 1940s, starting with a paper by Zipkin. It may not be so well known that there was a major emphasis on delay systems in the 70s and the early 80s, involving a large number of very prominent people that we know for contributions in other areas. In that period, many people were working on the so-called systems over rings, where the focus is on delay problems. There was another burst of activity in delay systems after the introduction of LMIs in the 1990s, but many basic problems still remain unsolved, and it's still a very interesting area. So, what are the main technical observations about delay systems? They're infinite dimensional. The state is not a vector, but a function or a vector of functions. The characteristic equation is not a polynomial, but it involves exponentials. And the stability analysis does not succeed with simple Lyapunov functions, but it requires functionals, integral expressions of some sort. Let me give you a flavor for what are the basic issues in control of delay systems through three scalar toy examples. So the first of these three examples, this is scalar. X is a scalar variable. This is a control. For d equal, when the delay is 0, this is an unstable system. When the delay is non-zero, this is a very easy problem. You can either cancel this destabilizing term using the measurement of the pass value of the measured state x, or you can actually dominate it using high gain. You don't have to exactly cancel it. The next problem involves a delay on the input. That's a totally different problem. That is a problem that the Smith predictor and various other extensions deal with. That can be a very hard problem. And I will talk about that one. The one that I will not talk about is a problem that involves simultaneous delay on state and control. Even when the state x is scalar valued, this can be a pretty hard problem, particularly if the delay on the input is longer than the delay on the state. And in the vector case, it's essentially unsolved at the moment. So I will focus on the second of the three problems. So I have to admit that before getting into delay systems, I had not learned about these problems gradually. I knew close to nothing. I was working on control of PDs and even didn't think that what I was doing would apply to delay systems. Simply because the results that I had up until that time were for PDs involving at least 2 derivatives in space, whereas the delay involves only one derivative, only convective effect. So I tried once, and here is how this went. This experience of mine, I think, is actually very useful. One can learn something and almost get excited about it. So let me now consider a vector problem, so a full general linear controllable system with delay on the input. Let me assume that the pair AB is controllable, and let me assume that I have picked some nominal control K to stabilize the undelayed system. Now, let me go ahead and replace the delay notation with a PD representation. So let me represent this delay subsystem using a transport equation. So this transport equation is given here, this PD. The output of the transport equation is the delayed input, and the boundary input into this transport PD is the actual control. So this is a very particular PD, sort of the simplest of PDs, and it can actually be solved in closed form if the input is given. So here's how the so-called backstepping method for PD goes. By the way, why think of this problem as a PD problem? Well, because it is a boundary control problem. I have a cascade of a partial differential equation U with an ODE x, and the input enters at the boundary x equal to d of this PD. So coming from that background, this is how you formulate this problem. And given that there are tools for boundary control in the context of this continuum or infinite dimensional backstepping, this is how you approach this problem. You approach it by constructing an infinite dimensional transformation, a continuum transformation of the state of the actuator state U into a new state W. This transformation, I'll tell you in a second what its purpose is, but its structure is a Volterra transformation. So this integral in y in the position y runs from 0 to the current x. So it's a lower triangular continuum operator, so to speak. There's also the ODE part in this transformation, which is crucial. So here's the objective. One wants to transform the original system into this target system using that transformation, and one wants the transformation to be invertible. So this target behavior, as you will see, now consists of a cascade of 2 PDs, but of a cascade of a PD and an ODE. However, the PD is now an exponentially stable PD. It's a transport equation with a 0 input. So this thing goes to 0 in d seconds. That exponentially stable system feeds into the stabilized ODE system. So that's the basic premise of this backstepping approach. So it turns out, after you plunge yourself into the algebra of determining the conditions when this transformation would achieve the conversion of the original system into the target system, you get these 4 conditions. So this is also a cascade configuration. You have, in blue, an ODE. Gamma is a vector of the same dimension as x, and a PD. Q is a function of 2 variables. You can actually solve both of them. The ODE just results in a matrix exponential, and the PD can be solved because of its simple structure given this boundary input. So you get explicit solutions for both of these things. Rarely do we get something like that for more general PDs like parabolic, second order hyperbolic, and so on. But for this delay problem, one can solve this explicitly. So plugging that in, here is the explicit solution of that backstepping transformation. Then that transformation is used also to pick the control. So the The control is picked from this condition in green, the boundary condition of the target system. As I said, you want your target system to be a transport equation with no input at all, so that its transient would vanish after d seconds. So that condition translates into a feedback law. So this u of d, that's the control input, and it needs to be defined as the rest in this expression. So I make that choice. So this is my feedback law. Let me now examine this feedback law. Well, first, let me rewrite this feedback law into a form that is not the PD-like notation, but the more standard delay-like notation. So this lowercase u of d is replaced by the input u of t. This state of the actuator is replaced by the past values of the control. And here's what you get. You get a feedback law the part in red is actually the nominal feedback. That's what you would use to stabilize the system for d equal to 0. And the rest compensates for the delay. So it should be no surprise that when you have delay, that this compensator tells you you need to use higher. When you have delay and when the plant is unstable, the compensator asks you to use higher gain, because this matrix exponential of an unstable system would result in that. Also, there's this distributed delay or integral term involving past inputs. So that is the infinite dimensional control law that this backstepping method leads to. Well, I did not know originally if this was something new or standard. It turned out to be something that had been invented in the late 70s and explained in a particularly crisp terms by Zvi Arstein, the same Arstein of the Arstein's theorem on stabilizability using CLFs. So this feedback has been known for quite a while, but without actually a Lyapunov function, and therefore without a proof of stability. Before Arstein, the people who actually came up with this compensator were Manicius and Olbrot in the late 1970s in the context of the finite spectrum assignment. But it all goes back actually to the Smith predictor. The Smith predictor idea was to use a prediction of the effect of the input on the plant in the feedback law to compensate the delay and achieve perfect response after d seconds. By the inclusion of this matrix exponential to account for the effect of the current state on the future one actually allows this predictor to work also for unstable systems. The original Smith predictor was a frequency domain idea. It was only about 20 years later, I believe, that Manicius and Olbrot developed this as a state space formulation, and it's sort of been used since very much in that form. So, what's the use of this new view of the predictor feedback? So the main new addition is a Lyapunov function in this constructive transformation of the actuator state. That is a large part of the state. You have an ODE and you have an infinite dimensional part of the state. Well, not having a Lyapunov function for what is 90% of your state is not having much. So the addition of the inclusion of the actuator state in the Lyapunov function allows for many, many nice things. So the first thing is a rigorous proof of stability using a Lyapunov-Krasovskii-like functional. So you see, this is the Lyapunov functional. It includes a quadratic finite dimensional part as well as this infinite dimensional part here scaled by x and appropriately scaled between the ODE and the delay part. So one can go ahead and prove that V dot is negative definite and so on. But that's not the end of the story. That way one gets stability in terms of this transformed actuator state, whereas one cares about getting it in terms of the original actuator state in blue. So to get that, one needs to use the inverse of the backstepping transformation, which can also be derived and written explicitly, as I've given here, and then using some L2 bounds on the L2 norms between these two infinite dimensional states, one can get an exponential stability result in this norm. So let me now step back and tell you where this all fits in from my personal perspective of boundary control of PDs and backstepping in general. So in the 1990s, backstepping was developed for nonlinear ODEs. We started working on extending this to PDEs of parabolic type first around 2000. And the first major class for which this could be applied that is physically relevant are Navier-Stokes PDEs. Then I started looking into second-order hyperbolic PDEs, such as wave equations and beams. And after that, with Andrei Smyshaev, we solved various problems of adaptive control for linear parabolic PDEs. So the first-order hyperbolic PDEs and systems with actuator delays, ironically, came after all this, although perhaps they could have come first. And just for the record, for the last couple of years, we've had also some results for some general classes of nonlinear parabolic PDEs with my former student Rafael Vasquez, who is at the University of Seville. So let me now talk about some other benefits of having a Lyapunov function. The first is robustness. I'll have to go fairly quickly through these slides, so I apologize that all the notation cannot be absorbed, but I will try to emphasize the things in words that are important here. So one benefit of having a Lyapunov function is that having designed a stabilizing feedback law, then you can pursue problems like inverse optimality. So you have a stabilizing feedback law, you can never, or it is rather very, very hard to find an optimal feedback law for an infinite dimensional system, but you can pursue inverse optimality, namely finding a feedback law that happens to be optimal with respect to a cost that you might care about, a cost that is quadratic. So that can be shown, and it can be shown in a rather unexpected and interesting way. It can be shown that if you add this lag transfer function in front of the predictor-based feedback, you get inverse optimality when C is sufficiently large with respect to a cost functional that imposes a penalty on the ODE state, on the distributed actuator state, and on the derivative of the actuator state. In other words, a penalty that sort of smooths the control action. That is not a surprising effect given that you introduce a lag filter, but proving it is quite non-trivial. And I'm emphasizing that C must be sufficiently large. You cannot put a really low-pass transfer function, then you would lose stability right away. But if you put a high bandwidth lag transfer function, you get inverse optimality without losing stability. The next result is very similar, but in the presence of a disturbance. So if you have a disturbance attenuation as a form of robustness to additive unmodeled effects can be shown both in terms of input to state stability with respect to the same norm that I showed before, as well as in terms of inverse optimality in a differential game sense. All right. I'm sorry that I'm not giving you much time to digest the previous slide. This one is really important. So, of all these forms of various forms of robustness, namely to initial conditions, to additive disturbance, there is one form of robustness that is particularly important, and that is robustness to the delay itself. So, if you're compensating the delay, and you get the delay, somebody gives you, or you estimate that delay value wrong, in the standard Smith predictor or in these modified Smith predictors, it's not obvious that this would work. And in fact, it's quite known that there are sensitivities to the delay error that are quite dramatic. To make things even more dramatic, there are results for infinite dimensional systems, such as second-order hyperbolic PDEs, beams, and wave equations, that show that those problems have zero robustness to delay. You take a exponentially stabilizing feedback, you add infinitesimal delay, you completely lose stability. Stuff pops up on the right-hand side in the complex plane. Why is that? That seems to violate our intuition from finite dimensional systems. Well, our intuition from finite dimensional systems is based on the system's right-hand side being somehow a bounded operator, which is not the case for some of the PDs. So having a robustness result with respect to a delay, I didn't really know if this held before spending some time establishing it. So it turns out that it can be, the following can be proved. If you have a delay error in the actual system relative to the delay length that you're using in the predictor, so in the predictor you're using d naught, in the true system you have d naught plus or minus delta d, it can be shown that for sufficiently small delta d error, you are still stable. Okay, now it's a lot of work getting there, but it is a very simple result. But here's one thing that needs to be appreciated. This result holds in both the positive and in the negative direction for delay. Typically, we have a system with no delay, we add some delay, we study robustness with respect to delay that has been overlooked. This is a result in both directions. In other words, both whether you've underestimated or overestimated the delay in your infinite dimensional compensator of the delay. So why is this kind of a pretty intimidating type of a perturbation in the system? It is because if you underestimate the delay, you're simply not putting enough feedback to compensate the system. But if you overestimate the delay, your feedback law inserts additional infinite dimensional dynamics that aren't there to start with. So I don't even know what kind of a perturbation that is. Singular, it is not, because it's some kind of an infinite dimensional perturbation. So it turns out this result can be established. And just to fully appreciate it, here's a corollary of this result. Suppose you suppose you have actually no delay in the plant. It can be shown that the feedback system can tolerate a small amount of completely unneeded predictor feedback. So for sufficiently small d naught, you will not lose stability by using this infinite dimensional compensation on a system that is finite dimensional. It just needs a finite dimensional control. All right, let me now say a few words about observer design with sensor delay. So suppose now that the delay is at the output of the system rather than at the input. And I've not included the control input in this problem just to keep the slides clean. It can be included in the design. It's no problem. So this is a system with a sensor delay. This is its PDE representation. And this is the infinite dimensional observer of the ODE state through the sensor delay, as well as of the state of the sensors, the distributed infinite dimensional state of the sensor itself. So this PDE-like observer can be implemented in this PDE form, or it can be massaged into another form that looks like an ODE, but it involves this delayed and distributed output injection here, which is the infinite dimensional part of the delay. Now this is non-standard. That I have not been able to find in past papers, like I've found the predictor control in the papers by Minitius and Olbrodt and Arstein. What you find in the past papers on observers for systems with sensor is the following idea. You estimate the state d seconds back, then you advance it d seconds in the future in open loop. So now dimensionally, that's the same. It's infinite dimensional observer just like mine is. But the conceptual is different. That standard observer is like your reduced order observer, where what's not included is the entire sensor state. The consequences, so the consequences are that it's going to be more sensitive to noise because there is an open loop component to that. All right, now let me get to the part which is only a few pages, but which basically captures my whole abstract. That's the application to nonlinear systems. So about 10 years ago, Andy Thiel proved a robustness result to sufficiently small delays for globally stabilizing nonlinear feedback laws. So what happens when you take a globally stabilizing feedback law for nonlinear systems and you have an actuator delay is that you first lose in the sense of the region of attraction, and then as the delay grows, you completely lose stability. But there is a robustness result that is sort of semi-global in the delay. This is not a design or redesign result, just an analysis result. Since Andy Thiel's result, there have been efforts in developing nonlinear control laws for nonlinear systems with delays. Much of it is for systems with state delays, not actuator delays. And these are some of the most prominent contributors, particularly Mirjan Jankovic from Ford. He has a whole set of very, very interesting results for various structures of nonlinear systems with delays. So let me now formalize this. So let this be an OD, a vector OD, so let Z be a vector. And let's assume that there is actually a delay. Let me also assume that a globally stabilizing feedback law, kappa of Z, is known for this system. So what do you do? How do you design a predictor feedback law for this problem? So let me say one thing. This is a nonlinear plant. So you do not expect things to be easy here. For linear plants, we needed an infinite dimensional feedback law. So this has got to be infinite dimensional and nonlinear on top of it. Okay? So here's what it is. So the feedback law, very interestingly, is given in terms of the original function or the original formula, but applied not to the current measure of state, but for the predictor of that state. And that predictor can be obtained using this integral operator representation. This, unfortunately, is not an explicit representation like in the case of linear systems. It is an implicit representation unless you know how to analytically solve every nonlinear system, which we don't. So it is infinite dimensional, nonlinear, and given implicitly. It can be calculated numerically, but this is what it is theoretically. I should also emphasize one big problem with nonlinear systems. Linear systems don't have finite escape. So in the presence of actuator delay, when the system is just waiting for the first values of feedback to kick in, nothing dramatic happens. The system runs in open loop, then the control catches it. For nonlinear systems, you can have finite escape in the first d seconds, and the things are over. So nonlinear predictor cannot be expected to hold globally. However, there are certain classes of systems for which global results can be obtained. One class is the so-called forward complete systems. These are systems that, despite being possibly unstable, do not have finite escape. What are examples of such systems? Well, many mechanical systems that we know do not explode in finite time. They have nonlinearities. These nonlinearities will involve a lot of trigonometric functions and so on, and things remain bounded for all time. So predictor feedback works in principle for those things. But it does not in general result in closed form formulas for the predictor. There's a special class for which you get closed form formulas for the predictor, and that is the class of feed-forward systems. Those were introduced again at Berkeley around 1991 in Andy Thiel's dissertation, and many people have worked on them since. The ball and beam example belongs to that class. The inverted pendulum actually does belong to that class, and so on and so forth. All right, I will show you one example that actually can have a finite escape. So, keeping it very honest, I'm taking a really bad example. Before the control kicks in, this scalar ODE could have had a finite escape. So, I apply the predictor in the way that I described on the previous slides. I will skip that. I think it's pretty clear. You basically run a predictor of that. I will skip these details. Let me tell you what the result is. The encouraging result is that you recover a region of attraction basically globally. If you do not escape to infinity over those first d seconds, the open loop period, the predictor feedback will achieve stabilization for all the initial conditions. The interesting part is the form of the stability estimates. So you see, L is basically the norm of the ODE plus delay part of the system. The norm is bounded exponentially in time, but not linearly in the initial value of that norm. You see, this lambda appears quadratically, and lambda itself is quadratic in this lambda naught, where lambda naught is linear in the initial norm, and so on. So there is a fourth order effect there corresponding to the presence of a quadratic nonlinearity in various transformations in this problem. It's worth asking the following question. All right, so what if my system does survive the first d seconds and I apply the uncompensated feedback? Will I be home free? The answer is no. So this can also be proved that even if the initial condition is such that you do not have finite escape over the dead time of the input, for sufficiently large initial conditions that fall within that set, you may have a finite escape over the next d half seconds. All right, let me now say a few words about adaptive control. I've had to trim down some slides to not go too much over time. So I've trimmed down some references. The adaptive control systems with delays, and specifically adaptive versions of the Smith predictor, have been developed by a few people, such as Anaswamy, Niculescu, Ortega, Lozano, and so on. The parametric uncertainties are always in the ODE, while the delays, no. The real interesting problem is when the delay itself is unknown, and on top of that, possibly the ODE parameters. But the delay, that's the hard part, because the problem is nonlinearly parametrized in the delay. At least if you look at it without the transport PD representation. So here is an adaptive controller for a system where the delay D is unknown. This is a slightly different representation than the one that I've used before. In this one, the convection speed is 1 over D, and D is unknown. So this is the adaptive version of the predictor feedback. D hat is an estimate generated from this update law. The details would require more time. I will skip them. But this can be designed, and it can be proved to be globally stabilizing in the following sense. So you do not expect global exponential or global asymptotic stability from an adaptive system. You get global stability. And for this system, you get global stability with this exponential estimate in terms of the initial norm. The norm captures the effect of the ODE, the actuator state, and the parameter estimation error. In addition to that, you get the regulation of the ODE state and of the actuator. So all of those things that you would want to get, you can get them globally with this design. The Lyapunov function is not standard. There are tricks in here that go beyond this compressed talk. So the Lyapunov function involves a log and so on, and various other things that I have to skip. I had a wonderful collaborator on a part of this project that came after this theorem that involved extensions to systems with unknown ODE parameters. French student Delphine Brèche-Pietric from École des Mines. And these are her simulations that, if one had time, show very interesting things. So this is the plant. It has actuator delay, well, delay, and it's open loop unstable. Scalar plant, just to keep it clear. So there are 4 segments of behavior, 4 intervals in time that are very interesting here. So the delay is 1 second. So over the first second, this is the state x. The state grows exponentially in open loop. Then the control kicks in and things start improving. Now look at the delay estimation error. This is for 2 different initial values of the delay. Basically, the delay is estimated quite well, or well enough, over the first second or so. The true value is 1, so you get pretty close. So, once the control kicks in, things start changing. But things start changing really to the better only after the delay has been properly estimated, which is at around 2 seconds, and that takes effect on the delay system at about 3 seconds. So it's only here that the system basically runs like a linear system. You see an exponential transient, whereas initially you see an exponentially growing transient, this nonlinear transient, and a linear transient of the system. So that's an adaptive system. All right, let me switch to some of the last comments here. So one can have a lot of fun with these. As I said, I came from the PD side, and now I went back to the PD problems. So rather than having a delay at the input, I've considered problems where you might have a more complex PD at the input, such as, for example, a heat equation or a wave equation. I could allow it in the actuator or in the sensor. So I've designed controllers and observers for all these problems. Heat equation to ODE, ODE to heat, wave to ODE, and so on. Let me just show you some of these things. So here's how the things change. Remember, in the delay predictor, this is the form of the feedback law. There's a matrix exponential coming here to amplify the measured state, and also in the control compensated part. Well, when instead of a delay you have a heat equation at the input, things get second order because of the second derivative in space here. If you want to see it another way, ask yourself, so what is the transfer function of this infinite dimensional actuator dynamics? For the delay, I know what it is. It is e to the minus sd. Well, for the heat equation, it is 1 over the cosine hyperbolic of the square root of s. So this would be really, really hard to guess. This feedback compensation is actually very intuitive. You're running the system forward d seconds. This is not. How would you guess what this is for dynamics that are not solvable analytically like the delay problem? I did this also for the wave equation problem. The wave equation problem is even more difficult because it's second order not only in x but also in time. So you see this matrix exponential is of this second order form, but with the state equation squared, so to speak. And there's no time to elaborate on the details of that. All right, so I've had even more fun, almost an unhealthy amount with these problems. I've looked at the cascades of PDs. First, a delay at the input, not of an ODE, but of a PD. This is an unstable PD, this reaction diffusion equation. So what is a predictor feedback for a PD? Well, this is what it is. It is given by a formula. And to compute the gains into this formula, it's quite interesting. First, you need to find the gain formula without the delay. This is this expression involving a Bessel function. Then you have to take that as an initial condition and run this for an equation that is the same as the plant over d seconds, and that's how you get the gain expressions for this system. So that's for a parabolic form. One can do this also for a hyperbolic equation. This gets more complex. This was done not for a wave PD, which is neutrally stable, but I've looked at it for an anti-stable version of a wave equation where you have all of the infinitely many eigenvalues in the right half plane on a vertical line. So that problem can also be solved using explicit gains. And then just a final bit of craziness is looking at a cascade of two PDEs, a wave equation with an unstable heat equation. So that also can be worked out, and some very interesting PDEs come up, like this beam-like PD with fourth derivatives, but for determining the gain. So anyway, I think it's pretty clear there is so much still in this area, and I'm talking about here about clean results, stuff that does not involve stretching problems, looking into robustness, but just finding basic solutions to these problems. There is so much one can still find in the area of distributed parameter systems and delay systems. All right, so now finally, let me show you one more thing that I like very much. So if you are not in mechanical engineering, or especially if you are in mechanical engineering and civil engineering, and if you don't care about this kind of problems, mechanics problems, well, shame on you. But what I've shown you so far is mostly motivated by mechanics, PDs, and other problems in electromagnetics. So you might not care about them after all, if your interest is mostly in robotics. Well, I want to show you that you still might care about them. So here's a problem in distributed robotics, or coordinated motion control, or swarming. And there was a talk recently in CITRIS that talked about network control systems. Here's a problem with a network of autonomous agents. So this notation here represents lowercase ui and vi is the position of an agent I. Capital U and V are the control inputs of a fully actuated agent in both x and y coordinates in a plane. So imagine a network of mobile robots. The standard thing that is done for this kind of networks is to induce some swarming behavior, some coordinated, intelligent-looking behaviors using simple feedback laws. These simple feedback laws typically are nearest neighbor-based feedback laws. Each mobile robot talks to two other mobile robots. There's some communication topology, which in the most basic case is a chain. And these robots apply these simple feedback laws, and yet they can induce some behaviors that are relevant, such as rendezvous or deployment into a line. So that's the problem. Most of this stuff works for deployment into lines, equidistant deployment between agents. The reason is that these feedback laws are motivated by a most basic principle for PDEs, the heat equation, the diffusion. Well, there are the other PDEs, and their behaviors would be worth exploring. For example, within the parabolic setting, this is the class of diffusion, advection, reaction equations. The continuum form is this. So in addition to the second derivative in x, there is the first and the non-derivative term. So we know how to control this kind of problems using boundary control. What is the consequence of that? Well, the consequence is that deployment can be induced into geometric forms that satisfy these general, well, second-order linear ODEs given here, which are parameterized in X, where X you should understand as the index of the agent, while U and V are the two Cartesian coordinates of each agent. So you see, this is the family of solutions of second-order ODEs. You've got exponentials, linear sines and cosines, and so on. So any combination of these functions creates various figures in 2D into which you can induce the agents to deploy. Just to emphasize, these agents use only slightly different feedback laws than in the standard methods. They just add an extra bit of this advective feedback and some of this diffusion feedback. So we'll show you these deployment figures. You will see I will deploy these mobile robots into things that are not straight lines, but curvy objects. So why has someone not invented this before? The reason is that the curvier it gets, actually these deployment profiles become unstable. So it's like, yes, there are all these other PDs, but they're unstable. My mobile robots will try to deploy into those configurations, but they can't stably. So how do we achieve that? So we achieve this with my new current student, Paul Freehoff. We achieve this by designating one agent to be the leader of the formation. And this agent acts like a boundary controller in a PD problem. And this agent monitors only one neighboring agent. He estimates the state of the whole formation, and he applies feedback. And he manipulates his own position to manipulate his neighbor's position, so that the neighbor influences his neighbor and so on. And in this way, a stable deployment is achieved into non-line type of configurations. So here's an example. This set of mobile agents starts from a rendezvous, starts from the origin. And then the leader agent, this guy in red, induces the deployment into this ellipse. So one can induce various other things, including, for example, a hyperbola, a spiral, and so on. In fact, I do have a movie that I would like to show you that takes you through a whole choreography of motions of this set of mobile agents. In this initial state, the dark straight lines indicate the communication topology between these agents. At each corner there is an agent, and the red guy, that's the leader. So starting from some random distribution of these agents, we first go into a rendezvous, then into a straight line. So that's standard. And from that point on, these are novel feedback laws for various figures. So these were two hyperbolas. They do not require any change in gains. The leader basically induces these changes in figures. So you just saw an arc on a circle and an arc on an ellipse. Now this is particularly hard, because this spiral, because it's a very, very unstable configuration. The agents need to have a feedback law that induces two unstable eigenvalues. This is a sinusoid, but distorted in the x direction. That can be obtained as a composition of a sine and an exponential. So back into a rendezvous before deploying into a figure 8. This again is quite unstable, but it's doable. So with that, I want to apologize for going a few minutes over time, and I'd be happy to take any questions.
Okay, thank you very much for the talk. Do we have any question for Miroslav?
Hi. So one of the questions which I want to ask about the form of the controller which you have. So you have a static gain and a prediction of the delay, two terms, right? So from an engineering point of view, like is there a relation between model predictive control? Because in model predictive control, what we do is that we synthesize control laws based on the predictions of the future uncertainties. So I think this might have some bearings on the predictions of the future uncertainties and the predictive control strategies which we use in process control, for example.
Okay.
And secondly, my second question was, can we actually increase the delay margins based on increasing the class of control strategy to be causal in the past states, especially if there is a delay? Because the current control law only actually uses the current state, does not use any past states which are there. So I was wondering if the delay margins or the robustness margins could be increased.
So the second question, possibly you're right, I hadn't thought of that. I'm not sure that I could provide a result in that direction, but perhaps something involving LMIs. You know, there is this whole community that postulates certain forms, applies the LMI formalism, and determines conditions such that such forms of feedback are stable. So that's a good idea, and maybe it would be successful in some cases. About MPC, let me just quote my colleague Bob Bitmead for saying that MPC essentially embeds a predictor into the solution. So I wouldn't say that this is the only way to do it. It's a clean way to do it, though. And for PDs in particular, well, I guess at this point it's the only way to do it.
So I think we'll have to stop because we're out of time, but I wanted to thank you, Miroslav, for coming, and in the tradition of the Nokia Distinguished Lecture on Cyber Physical Systems, we're going to give you this little memorial.
Thank you very
plaque.
much,
So thank you very
Alex.
much all for coming.